Good morning, everyone. My name is Hao. I'm from the RCS lab at the University of Waterloo, Canada. And today I'm going to present our work, HATCP, a reliable and scalable framework for TCP network functions. And let's get started. Packets often traverse different network functions for processing. Network functions, or NFs, are the basic building block for networks. The failure of NF often leads to large-scale service outages, and because of that, it makes the failure of NF expensive. Network functions are widely used in networks. To improve their reliability and scalability, we need a framework to provide failover, migration, and load balancing. For all the network functions, we broadly categorize them into two categories: the layer 2 to 3 NF and layer 4 to 7 NF. For layer 2 to 3 NF, they often operate on individual packets. The common examples are firewalls, intrusion detection system, and NAT. And for layer 4 to 7 NFs, they often rewrite the TCP flow, and the common examples are accelerators, proxies, or TLS terminators. The state replication systems are designed to improve the reliability and scalability for layer 2 to 3 network functions. They often assume that the state updates are small and infrequent, and they are using batching to reduce the replication overhead. However, these systems cannot be used for layer 4 to 7 network functions, and this is because the combination of increased size, frequency, and complexity undermines the batching techniques used by these systems. TCP is ubiquitous. It makes up the majority of the internet traffic. And because of that, we need a better solution for layer 4 to 7 network functions. Because of that, we introduced our solution, HATCP. HATCP is a framework that is designed for layer 4 to 7 network functions. Developers can build their NF on top of the HATCP framework. And if we look at the internal of HATCP, it is a separate module that is built on top of the TCP stack. And it didn't modify the TCP protocol, so it's completely transparent to the client. HATCP uses active replication to keep the state in sync. In HATCP, we have primary and replica. HATCP will actively replicate all received packets from primary to the replica. And both primary and replica will process the packet inside their local stack in order to construct the same state. Now I will show you how does HATCP work during the steady state processing. When the primary receives a packet from client, it will first duplicate this packet and then put the original copy of the packet into its own packet queue. And then the primary will send this duplicate copy to the replica. And once the replica receives this copy, it will first also put this duplicate packet into its own packet queue and then send an acknowledgement back to the primary to confirm the reception. And then both primary and replica can start processing the packet. And for the primary, it can just take the packet from the packet queue and then deliver it into the TCP stack. But for replica, it can only deliver the packet when it meets the criteria. HATCP uses packet queue to hide the performance differences between primary and replica. All incoming packets are appended to the back of the packet queue to enforce the ordering, and then later HATCP will deliver them into the TCP stack. If the replica is falling behind with the packet queue design, it allows primary to keep processing the packet without waiting for replica to catch up. And this improves the throughput and tail latency. Because HATCP allows replica to fall behind, then the replica may receive a packet that acknowledges the data that hasn't been sent. And normally, if we deliver this packet directly into the TCP stack, it will cause the packet loss. Or it rejects, the TCP stack will reject this packet. To solve this problem, one solution is we can always copy the packet before we deliver it into the TCP stack. However, the packet copying is very expensive. So instead, HATCP only delivers the packet when the TCP stack is available to process the packet. For example, the TCP state in the packet header has to match the expected value from the TCP control block, for example, the sequence number and the acknowledgement number. And the TCP stack has to have enough space to take the packet so that the packet won't overrun the TCP window, and etc. When failure happens, HATCP allows replica to take over the primary seamlessly. And this is because HATCP uses active-active replication, so the state in primary and replica is always in sync. During this process, for replica, it only needs to drain the packet queue if there's any left over and take over the IP address. And afterwards, it can just continue the service. To integrate the HATCP into your application, you only need 3 lines of code to enable it. HATCP only replicates the network stack state, so it guarantees the identical network input. In order to let HATCP work properly with your application has to follow the output determinism programming model, which by giving the same network input, it will always generate the same network output. For all the applications and benchmarks used in our paper, they all follow this programming model. And alternatively, you can also use the record replay or the state management system. HATCP's performance goal is to support 100 gig link. And in our first design, we use TCP protocol for the replication channel. And this is because it's relatively simple to build and it handles packet loss and packet retransmission. However, with our first design, we can only achieve 54 gigabit performance. To improve the throughput, we have to address 2 challenges. First, high overheads. Experimentally, we're seeing a high CPU usage on the TCP encapsulation and processing. And second, we're hitting the TCP over TCP problem, which is as known as the TCP meltdown problem, where the congestion control algorithms may disagree on each other and cause the performance instability. To solve this problem, we decided to switch to the IP protocol for the replication channel. By switching to the IP protocol, we are losing the reliability and optimizations provided by the TCP protocol. First, for the reliability, because we are using the IP protocol, so it doesn't have the ability to detect the packet loss or do the packet retransmission. But our observation is, for the active-active replication, it's mainly designed to be used in a local area network. So the packet loss rate or the congestion level is much better than the WAN environment. And because of that, we are relying on the client to retransmit the packet for us. For example, if there's a packet loss in the replication channel, then the primary will never receive the acknowledgement from the replica. So it won't process the packet, and over time, the client will retransmit the packet. This helps us to simplify the design, and also it forces the TCP congestion control algorithm to adapt the overall link quality between primary and replica. By switching to the IP protocol, we're also losing all the optimizations provided by the TCP protocol. For example, the TCP RO, the large receive offload, or TSO, the segmentation offload. Our main insight here is, for most of the stack, their performance is proportional to the packets per second instead of a gigabit per second. And by collapsing multiple smaller packets into a larger one, we significantly improve the performance. And experimentally, we're seeing a 6.2 times improvement on performance with TCP RO. Because we are using the IP protocol, so it turns out we can use the IP fragmentation, which is also used by UDP protocol for larger packets, to achieve the same optimization. However, by using the IP fragmentation code, it brings in one more challenge, which is the IP collision problem. The IP collision problem is documented in an RFC document. Without a good solution to this, protocols such as QUIC or SCTP choose to not use IP fragmentation. And experimentally, we're seeing about 200 collisions per second at 25 gig with multiple connections. And the problem is, in the IP protocol, it uses a 13 bits fragment offset field to indicate which packet this fragment belongs to. However, with multiple replication channels and high throughput, this number will collide with each other and cause the packet loss or even the data corruption. And this will in further leads to the congestion control algorithm on the client to reduce the bandwidth. In order to address this issue, we introduced a new IP option called Stream ID. Stream ID uniquely identifies the fragment between different replication channels. It guarantees that the fragment will always be stitched to the same flow, and it completely eliminates the IP collision problem. Along with other optimizations, and finally, we can achieve our performance goal. HATCP is built on top of the FreeBSD 13.1 kernel, as well as the F-stack. And this chart shows the breakdown of source lines of code in each part of the system. To evaluate HATCP, we use the 3 macro benchmarks and several application benchmarks. And for the rest of this talk, I'm going to go through all the micro benchmarks. For the setup, we use the dual Intel Xeon processor with 100 gig Mellanox ConnectX-6 NIC. All nodes are connected to the same 100 gig switch, and this represents the worst case scenario because the latency between primary and replica is identical to the latency between primary and client. For replication overhead, this represents the worst case scenario for HATCP because primary the primary gets the receive bound traffic, and it has to replicate 100% of the traffic to the replica. And in this graph shows the performance change during a 1-minute run. And you can see that by adding HATCP, the performance remains stable, and experimentally, it only decreases throughput by 3.4%. For latency, we use a replication server with a load generator that issues 100,000 QPS load. And we use another node that issues 1,000 requests per second in order to measure the latency. And this also represents the worst case scenario because all nodes are connected to the same network switch and they are all in the same network. If we plot the added latency to this graph, you can see that the added latency is pretty low, and the tail latency is also well controlled. And this is because we are using the IP-based replication channel, which is very efficient. For migration, we compared HATCP with 2 other recently published research systems, Prism and Capybara. And for fairness, we only kept the TCP migration part in the other system. And in this graph, the orange bar represents the network communication time, the purple bar represents the operation spent in TCP stack, and the teal bar represents the system-specific operations. And for the purple bar in HATCP and Prism, they are significantly higher than the other system. And this is because HATCP and Prism, they are using FreeBSDs or Linux network stack, which is more complicated than the custom stack used by the other system. And in this experiment, HATCP can migrate a connection in 38 microseconds, and Prism needs 90 microseconds, and Capybara needs 65 microseconds. For the failover, we only tested the HATCP because the other system doesn't have the same feature. In this experiment, HATCP can migrate a connection in 300 milliseconds. This time is significantly higher than the migration, and this is because experimentally, we're setting the failure detection time to around 300 milliseconds in order to minimize the false positive. In conclusion, HATCP is built on top of the production-grade network stack. This is hard because FreeBSD's network stack consists of more than 150,000 lines of code, and the HATCP by itself is more than 10,000 lines of code, which is even larger than some of the research TCP stack. In our paper, we have more discussions about different challenges, optimizations, and benchmarks, including a distributed load balancer. And please refer to the paper for details. All our code will be available at this address. And that's the end of my talk, and thank you very much for listening, and please let me know if you have any questions.